Students will discuss another tool what is known as line, surface and volume integrals. So these integrals again makes us richer by knowing this, because we are using them in the next subsequent topics. Before I discuss what is called as curl of a vector, I thought that line integral, surface integral and the volume integral, the knowledge about line, surface and volume integral is must to know curl of a vector. So let us say line integral of a vector. So let E of x, y, z be a vector in a vector field. Fine. We'll draw any curved line like this. A curved line. Say this curved line is AB. AB is any curved line which is drawn in a vector field. Keep in mind. Okay. Now I'll take a small element of this of length dl. dl is its small elemental length dl. I'll call it as P and Q. Right. I will draw the tangent to this, and this is the electric vector E is directing, which makes an angle theta with this. That is, so AB is a curved line, a vector line. We have mentioned thus that a vector field can be represented by a vector line, means a curved line. We have taken a curved line here AB, and we have taken a small elementary length dl, which is between P and Q, and we have drawn a tangent here which indicates the direction of electric field. In fact, in a vector field, E is the vector represented by this line, the curved line, and at this point this vector is acting in this direction, and it makes an angle theta here. So if I move a charge from P to Q, a unit charge, a P to Q in an electric field, so the work done on this charge, charge is equal to, say, dot product of what is called as say E, that's one, E dot dl. Our work is nothing but force into displacement, like that. So E is the electric field vector or vector E, and dl is the displacement here. So this will be equal to E dl cos theta. E dl cos theta. So let me write this E dl cos theta. We have taken this. So what my point is, if this electric field vector or a vector E is varying in both magnitude and direction from point to point, this point, this point, this point, point to point, then we can represent this as an integral, that is integral from point A to point B of this E dot dl, that is equal to integral A to B E dot dl or E dl cos theta. Right. Here It is called as line integral of a vector E. It is called as a line integral of a vector E. Point here, a line integral which is taken from A to B for all the points. Normally we do this, we divide this line into small portion or any curve into a small portion and then sum them from this point to this, we will get total. Similarly, here we have divided this a vector field or a vector line into small elementary lengths and then we have taken sum of that. Because it is a continuous, so we have taken integral from A to B, that is E dot dl. E dot dl is a work, right? When we say if work done, so this is, if it is independent of path, if I write this, say, okay, this is small a, this is small b, whether you go to A to B or B to A, if it is independent of path work, if you calculate, that is, we call it as conservative field. And if it is dependent on path, that is like this, as we said, it is non-conservative field. Right. So we can write, say, in this case it is not dependent but it is from beginning to end. If I write the integral A to B E dl cos theta or E dl here, this is from, not for all the points here as we have defined here, but it is from A, the beginning point and the end point. It doesn't depend upon the path. That field, it gives us conservative field. So we are integrating a vector. We are integrating a vector. If it is depending on the path, then we calculate for each point the integration and we call it as a line integral. Suppose the limit, this line integral can be written it as a closed integral like this. So closed integral, that is A to B, or it is written as, when it is A is equal to B, it starts, path starts from A and it may end with A. So here it is a closed line integral. It is indicated thus. You can write this integral A to B, say E dl, okay, and say another integral, that is B to A E dl, right, this is equal to 0. You are starting from point A, going round and coming to the same point. So A to B and B to A, this will be 0 here. So we got an idea here by saying the line integral of a vector. We have considered a vector in a field. We have drawn a vector line in the field. We have divided that line into small segments or elementary lengths, elements, and we have taken the length AB here. So initially PQ is the small segment or elementary length which makes an angle theta with, say, the direction of vector. So when I move a charge from P to Q, the work done on that charge is E dot dl. E dl cos theta. Now, if this electric field vector is varying from point A to B, that is simultaneously both in magnitude and direction, that variation of vector from point A to B is represented by an integral, that is A to B E dot dl. And this line integral of a vector gives us a scalar quantity, So here, this closed line integral, if the line is open, we can write like this. If its line is closed, we can write this. Okay, the line integral. So the line integral gives us about in which field it is working. If the line integral is depending on the path of a line, that is path of a vector line, then it is called as non-conservative field. If line integral is independent of path, it depends only on the initial and the final point, then the field is called as conservative field. See how beautiful this is. It gives a lot of information for us to go for what is called as Maxwell's equation. I am using the word mighty Maxwell's equation, which is the core portion of our syllabus. Let's go for another integral called as surface integral. This is also called as surface integral. Fine. Say flux of a vector. Surface integral or a flux of a vector. Let me draw any closed surface here. It looks like kidney. Any state, no problem. Okay. This is a closed surface in the vector field. Okay. I will divide this closed surface into small elementary surfaces like this. Say I will take a small elementary surface ds. I will write this as ds. Fine. To this ds, I will draw a normal, and this is unit vector L. Okay. So this ds will work as, say, area vector. Ds works as an area vector. Depending upon this, ds is the magnitude here. That is n unit vector n ds. Ds is the area, and it is called as area vector. What I have done, see, I have taken any closed surface. I have divided that closed surface in a vector field into small elementary areas. I have picked an infinitesimally small area ds. I have drawn normal to it, and that normal is a unit vector. Here, this area of the ds is the magnitude. It works as an area vector, and its direction is acting along the unit vector. We got this as area vector. In fact, to be frank, that area is a scalar quantity. Many a times we refer this, we convert that area into vector like this. Now, if I take a vector, any vector at the middle of this elementary area A, and say this area vector, say vector A, and this vector A makes an angle theta with a normal. Makes an angle theta with a normal, then I'll write this a double integral. Okay, and it is written S that is area, that is vector A dot this vector ds, and this we can write it is equal to double integral, that is or S. It is called as surface integral. Surface integral A dot n ds. N dot, it is ds here. So this we can write it is equal to, say, surface integral A cos theta ds. Theta is this, ds is this. The surface integral is defined as a flux of a vector, to mean by literally flux. Flux are the number of lines crossing a unit, a element of certain volume per unit area. The number of lines crossing per unit area is called as flux. We measure it, and surface integral gives us a flux of a vector. It measures how much flux is. You can give, say, an example here. A fluid is flowing. Fluid is flowing, and say the fluid, when it is flowing, right? So you can calculate the flux of the fluid as we have done in the earlier example. So that gives, or that measures the flux of a vector. Here it's a flux of a vector. It is indicated by double integral in order to differentiate from the line integral. Line integral is a vector, and flux integral, that is flux of a vector or a surface integral, gives us the flux of a vector. Normally, instead of writing this, they write, instead of writing double integral, we write S. Okay, S is nothing but a surface integral. This is what we have to speak about a surface integral. Well, let us go for a volume integral. So, to find out the volume integral, so let us consider a closed surface again, and then we'll have here a volume element of this kind. You can draw it. Something like this. Okay, this is volume element dV. A surface, closed surface, enclosing a volume element V. Now to write what is called as, if AB is some vector here, A is some vector in that volume element having volume dV, so then the integral we can write, that is triple integral. It is called as volume integral, that is AdV. AdV is called the volume integral of a vector A or the volume V in a closed surface S, or even in open surface. Normally this volume integral, instead of writing it as a triple integral, we write this way, V. V stands for volume integral, as like S stands for, say, surface integral, and say for a line integral we can write a closed line integral, a closed surface integral, and a volume integral. We are making use of these integrals to explain some of the other factors. Let me go for the important article, that is curl of a vector. Curl of a vector and its physical significance. Curl of a vector, it is written as C-U-R-L of a vector. Let me take curl of a vector. Say, fine. Any vector we can write curl of a vector, or a curl of a vector field. Let me curl of a vector field. Right? Yes. Well, or to start with its definition, before I define curl of a vector field, it is a vector. It gives us a vector. Gives a vector. Curl of a vector field is a vector. Gradient of a scalar is a vector. Divergence of a vector is a scalar. Divergence of a vector is a scalar, and curl of a vector field E, it's a vector. Curl of a vector is a vector. Well, I am going to use the word lambda, L-A-M-E, this may be E, L-L-A-R, lambda or non-lambda. What do you mean by this? See, the line integral gives us an idea about whether the field is, say, conservative or non-conservative. Here, if the field is irrotational, vector field or vector, if it is irrotational, non-rotating, then it is called as irrotational, then it is called as lambda field, or it is a conservative field. We need this conservative field. Somewhere we define this lambda field or irrotational field or conservative field. Sometimes while reading we come across this term. This is non-lambda field, what is called as non-conservative. Non-conservative field. Irrotational or non-conservative field, conservative field, non-lambda or non-conservative field, or rotational here. Now, if I take a line integral of a vector, say closed line integral of a vector, say A, dl, and if the closed line integral of a vector A is 0, that means line integral of a vector in a field called as conservative field around a closed path, that is C, around a closed path is 0, then that field is called as conservative field, right? If the line integral of a vector is around a closed path is not equal to 0, then the field is called as non-lambda field or a non-conservative field. And this we have seen just now when we have discussed what is called as line integral. Only thing I have introduced to you these two new words. Let us define curl of a vector. So curl of a vector is defined in terms of line integral, and therefore I have discussed those. The curl of a vector in a vector field at any given point is defined as a vector quantity. Curl of a vector is a vector quantity whose magnitude is equal to maximum value of a line integral per unit area. Maximum value of a line integral per unit area along the boundary of a test charge. We'll discuss this by drawing. I have defined it. Let me clear this. This is some surface. We have so many elementary areas here. These are so many elementary areas I have drawn. Fine. I'll take some point P, and here I will draw a normal to this, that is N, and ds is the area. Let's say this is point P. Okay. If I draw at this point some vector, say A, let me draw this vector A. Okay, around this. This is elementary area as we have done. So A is any vector and ds is an infinitesimally small surface area vector with n, a normal here. So curl of a vector, C-U-R-L, curl of a vector A, let me write its magnitude. I have taken the curl of a vector is defined mathematically. Limit, say delta S tends to 0. So this is closed line integral of A, say, and dl. Its maximum, that is per unit area of this surface area. Let me explain this. We have written mathematically, curl of a vector is a vector and it is defined as the maximum value of a line integral per unit area around a test area here, that is, say it's a limit, and this curl of a vector A is a vector. It is equal to limit delta S or ds tends to 0. Let me write ds tends to 0, the maximum value of the closed line integral A dot dl. It is taken over the closed path A dot dl divided by the area of this say elementary or a test area ds. This is mathematical definition which we can define it in terms of words, that is curl of a vector field is a vector which is defined as the maximum value of a line integral per unit area. So area being the boundary, that is in a closed boundary, you can say. That is the definition of curl of a vector. This can be written in different notations. See, curl of A dot n, that is limit ds tends to 0, the line integral, closed line integral, that is C A dot dl by ds, where n is a unit vector along normal to the test area here. Now we write this expression in using Cartesian coordinate. Let me write that using Cartesian coordinate. Let me write curl of a vector v that is equal to del cross, it is denoted as del cross V. Curl of V or del cross V. We can write this as using matrix notation, say I, J, say K, dou by say dou X, dou by dou Y, dou by dou Z, and then we can write its magnitude Vx, Vy and Vz. Okay, so we can simplify this, that is using this I can write I into bracket dou Vx, that is dou Vz here, dou Vz upon dou Y minus dou Vy upon dou X plus Z dou Vx upon dou Z minus dou Vz upon dou X plus unit vector K, say dou Vy upon dou X minus dou Vx upon dou Y. Check this. Note that curl of a vector is a vector. It is denoted by del cross V. V cross del is different. Let us go for the physical significance of curl of a vector. We can complete this. Physical significance of a curl of a vector. So, curl of a vector indicates in fluid dynamics. Fluid dynamics, we can write it as curl means, say rotation, say sometimes it is indicated rod, or what is called as circulation. The fluid vector, that is velocity vector, has some, say circulation, has some rotation. That means, see, this is 1, this is 1, this is 1, this is 1. Say in another way, this is, say this is, and this is. A fluid vector has some rotation or circulation, that is maybe in a downward or in upward, that we can say verticity. We write it as a verticity. So the line integral of such a vector, that is closed line integral of a vector A, say dl, is equal to 0. That means closed line integral